Log on, tune in, find out. Another good idea from Cambridge.
When I first heard your name, which was I was introduced to you by Luis Tenorio, I thought he said your name was Omre, which is Spanish for man. You are an hombre, after all.
He's not a man.
Anyway, the title of his talk is Spatial Categorical Inversion.
Okay. I'm glad to be here, and I spent a couple of beautiful weeks at Cambridge, and I'm now going to talk about spatial categorical inversion, which is of interest to a lot of people in Norway. It's petroleum related, but it also draws heavily on seismic. I have two co-authors, that's a PhD student and a geoscience person, and there are a lot of references that you can find in papers. What I will do actually, what I'm trying to do is I'm trying to identify, not identify, I'm trying to compute hydrocarbon volumes. I don't know what this is, but can I remove that? By what? Move the cursor. Can I? Okay, that is Lisbeth from Fortset. Here we are.
So the bug is with you, not the
Okay, here we are. So, I will. I'm after computing the volume of carbons, oil and gas, and this is some kind of a artistic view of how that look down. And I am a statistician. I have a real case study. I have abundant of real data, and this is some sort what I think statisticians should care about. So here we are. This is the volume that I'm looking in, and there are actually 2,000 meters below the seafloor. I have discretized it into a grid of 900,000 grid nodes, so there is some resolution. I have seismic data you will see later on, but I also have information in one well. So that was the first well they were drilling, so they identified hydrocarbons. I will use that one single well, the 5 other wells I put aside, and use a blind test for my predictions later on, which is a dangerous thing to do in the beginning, but since I'm presenting it, the story is fairly successful. Yeah. So I have to parameterize my problem to some sort, and since this is discrete, I look at shale and sand, and in the sand I have 3 fluid filling. I have gas, oil, and brine or water. So that means there's some kind of almost a hierarchical model, but I treat them as 4 alternative classes in every spot. And if you then look at my problem, this has quite some sample space. 4 to n, which brings me up to 10 to 533,000 size. And that simply means it's a combinatorial problem of some size. Yep. You don't want to look for the optimal solution by just checking. Porosity is also in here, but I'm not going to make a big case of that. I'm going to treat this in some kind of a Bayesian setting to have a formalism to put this together in. And since I'm in statistics and probability, I will try to assess the full probability distribution. I had to start off with a prior on my discrete process in space and also porosity. I will have to link up my observation to likelihoods. These are the building blocks. And my observation will be seismic and that one single well. And then, of course, multiplying these together, having a constant, normalizing constant, gives me the posterior. A lot of mathematicians are also treating this a little bit similar, but often they just ignore the constant because they look for the mode only. Huh? So that falls out and you look for the maximum of this. I am very much concerned about the constant because I want to model the full probabilistic setting of this 3D reservoir. And of course, computing that by just summing up is not a good way to do it. Start looking at the data. I use seismic data, but I must, of course, admit that it's been doing a lot of seismic processing. So what you have seen previously from Mulder and from Martin de Hoop a lot of this migration correction, multiple removal, and refraction has been taken out already. So I use something that is called seismic AVO data. That means it's amplitude versus offset. So that means and they are on common depth point. So if I look in one point here, the amplitude is the same, and they come from 3 different angles up here. So they have some sort been able to shift things around in space, so I get the reflection from one spot, but from different shooting angles. That makes the problem much easier in many respects, but still challenging. If I look at my well data in that one well in the middle of the reservoir, I have, of course, these 4 classes, sand, shale with the fluid. I have taken cores in that one well, so I know the truth. I know P wave velocity, S wave velocity, and density down in that well, and I know the porosity down the well. And intuitively, I will of course use that for calibrating my model later on. I will set up a model involving these variables. I will calibrate it against that well, and then I will try to use that out in the rest of the reservoir, which will be a meaningful thing to do for a statistician. Yep. So my model is like this. What I'm after, I like to predict lithology fluids given my data. This is it. But to link this up to some kind of known physics, I'm putting in 2 nuisance parameters. One set of, here is my lithology fluid, here is my data, well data and seismic. I put in 1 nuisance parameter, which is the elastic material properties. Pressure, P wave velocity, S wave velocity, and rho. It's of no interest as such, but it's nice to have in my model when I build my model, and I integrate it out afterwards. I put in my model parameters as nuisance parameters because I want them to be stochastic. I don't know too much about my rock physics depth trend because the reflection from seismic varies with depth, and I don't know that exactly, so I like to build in the uncertainty of that. I don't know my wavelet exactly. I like to build in the uncertainty of my wavelets. And most of all, I don't know the signal to noise ratio in my seismic data because it's been going through a lot of processing. So I want to have that as a stochastic variable that I'm randomizing over. And you see, I'm integrating out that afterwards. So then what I do, I actually do the parameters up here. I estimate them from the single well, information in one well, and later on when I predict the lithologies, I do that only based on seismic data. I could integrate all the data in this process if I want to, but since I like to see how well I match the well, I've chosen only to use seismic data in this process. I will talk mostly on this and give you the results from the other. Then I have to start the model building. I have to start to link my data to what I'm interested in. Here I go from pi. I have 4 classes out in this big space. If I knew that, what would the elastic material properties look like? What would VP, VS, and rho look like? So I have to make a rock physics model, forward model, and I have to take a model from the elastic material properties into my AVO seismic data. That's the reason why I put M in the middle, because these are blocking up my problem into pieces that I know that physicists are working with. If I didn't have M, I had to do the step from discrete lithology straight to seismic data, and that would be too complicated. I will not follow the line of research or the line of knowledge in the community. Now let me look quickly at this one. What happens is, for each lithology, I need to estimate 3 variables, VP, VS, and rho. And here I have my seismic data. Here I have well number 1. In this area, I do this calibration simply, and I have some depth trends in the elastic parameters. If you look at P wave velocity, you see that this line is actually what comes from shale, is fairly constant with depth. if you look at sand, it varies a lot with depth, and you see that the three fluid fillings are some kind of separated by the Gassman equation. You know how to do fluid substitution in the rock physics models. The reason why there is a kink here is because at that stage there has been some metamorphic behavior in the rock. From being grains that were loose, you had some cementation. So at some stage a chemical process just bind up the frame, and of course the response is very different. So it's important to identify this depth here. So what I have then, at every depth I have three variables, and I have some kind of a cloud of uncertainty of rock that varies down. And you see that here I have, this is a three-dimensional plot just projected in, and here you see this is the shale, which is fairly constant. These are sands with the three fluids, and you see they are elongated when I project it down because they changes with depth. But later on I use them at the depth where I like to classify, so I have different models for different depths. So that brings me from one lithology, say gas sandstone, then I go to the red one, and then in this probability distribution it gives me the distribution of the amps. So there is a uncertainty in that rock physics model also. Then I go from elastic parameters to AVO, and there is here it's important to since there are so many people in geophysics, it's important to be pragmatic. I mean, you have to give and take in your model. You cannot believe that that your model is the truth. You can simplify, but you can always make it more difficult. So if you have the true model, it will be like a Dirac in a probabilistic setting like this, but all of the time we are using simplifications, and I use a lot of simplifications because I like to obtain more in other aspects of my model building, for example in my prior. If you look here, I use a simplified relation between the elastic parameters and my AVO data, but then I have to compensate with an error term. And since I calibrate my model in the well, I can assess the uncertainties in the error term. So that means I only appreciate my data less by using a simplified forward model. And you're free to do that because then you get larger uncertainties in your predictions. So this is what I do. You recognize this. These are the elastic material properties. Different angles. You can identify P wave, S wave, and rho. And the relation here is as such. The elastic parameters, this is the contrast operator. This is the separates matrix. And you see that this model is very simplified. So I have an error term in there. Then I have the wavelet, which is some kind of a convolution of the signal that applies both to the model and to the error term. That means I got a lot of colored. Actually, later on, I proved or showed that I have 99% colored noise with the same frequency band as the signal, which is complicated to some sort. But this linear model is what I'm using up here, and I say that it's independent from one to the others. That's why I call it product there. So when I do estimate, calibrate it, I get these are the wavelets. They are about 40 wide in my gridding, and this is a scaling parameter that I have estimated. And if I look at the signal to noise, when I build my model the way I have with the simplified likelihoods, everything, this is the signal from the known lithologies in the well. This is what I observe in the seismic along that well. And when I look at that, I have a signal to noise ratio of 1. It's 50% noise in my data, and that I have to live with. And of course, that's not very promising if you like to solve an inverse problem. But still, this is how my model, that's what my model gave me. Now I have been able to link my lithologies over to the data. I had to look at the prior model, and that's the critical step. Discrete processes in space are difficult. There are few well-established ways but we have Markov random fields. 3D Markov random fields. And that means if you are in one point in space, given the rest, the probability for the event in one point, given the rest, is only dependent on the neighborhood. So it's some kind of a localization model, that you have many local models that add up to a global model. But if you try to do that in 3D in the regular standard way, you fail, because you have to parameterize it very smartly to be able to get that converge in finite time. So what I do a profile Markov random field. If you look at the top sphere, I look at the neighborhood, the probability in that profile, because this is the profile that goes down in time, is dependent only on the 4 closest ones. If I then tilt the picture, it looks like this. So this one will be that one will be that, and this is the t along the depth. I say that the profile here is only dependent on those two. And I parameterize it such that this profile is a Markov chain when I go upwards, a non-homogeneous Markov chain. So the probability for what happens there is dependent, first of all, on the two neighbors here, because it's non-homogeneous, and then dependent on what's below. So I can model some sort the ordering of my faces vertically. So what do I do? First of all, this is the same picture. The two neighbors, they are coming in like this in the expression, and I only put on some numbers on them because that says something about the horizontal smoothness. And you see by the picture of concepts, there is a smoothness horizontally. Then this is a transition matrix for the Markov chain that goes upwards. And this is more complicated. If you look at this, it's obviously not too much ordering in sand and soil, but in the fluids, they are sorted. You never, always gas on top. So if you look at the transition matrix here, from shale you can go anywhere. From water you can go anywhere. From oil you cannot go to water. And from gas you can never go to water or oil. So this ordering, I enforce that by 0 probabilities in my model, and that means my prior is really having a lot of nasty domains of 0 probabilities inside the sample space, which makes it very difficult. You cannot start walking around in a sample space because you will then never get around these areas. You have to be very smart in how you sample when you are in settings like this. And at the same time, if you show a model like this to a geologist without this ordering, they won't trust you. So then, what I have then, I have the Gibbs formulation. I just wrote it up. A statistician will see it immediately. This is the prior. These are the likelihoods, integrating out nuisance, and so on. And you have the corresponding Markov formulation, one spot given the neighborhood, but then you have to give it for all points. And these are lend itself easily to Gibbs sampling, which simply means that in the space laterally, I go and sample one spot at the other, given the neighborhoods. So I have one spot given the neighborhood, and once I've come to a given point, I simulate the profile. But simulating the profile is the hard part. That's where all the 0 probabilities are. And they look like this. There is a non-homogeneous sequence of lithologies up here with complex 0 transitions. So if I start taking out one and try to put in something else, I very often hit non-0 probabilities. So I have to do this jointly. First of all, I'm able to integrate out M analytically. So this is what it looks like. But then my wavelet, the seismic wavelet, is actually 40 wide. So there's a lot of coupling of the data. And simulating from this is very complicated. If I throw out the wavelet, I just imagine that the wavelet is only 1 wide. Then I have a model like this. So you could imagine just throwing out a wavelet. If I have a hidden Markov chain like this, I can solve this exactly by the forward-backward algorithm and get the probability model exactly, which is a non-homogeneous Markov chain, and everything is good. But if I do that, I get terrible results because the smoothing and the wavelet is so important for mixing up the information. So the idea is then to see if I can reformulate this in a sense that I'm putting up linear combinations here and I'm changing the relations here such that I get it on this form, but at every point I have all the data. So if I can reformulate it that way, I may be able to do things fast. And I have to be quick. This is some sort where you do this. And if you look at this is the likelihood going from pi to d. This is going from pi to m, and this is from m to d. This is easy because it's on multiplicative form. We want this to be on multiplicative form to get the graph I showed you. But it looks like this. It's Gauss linear. You have the data minus, and then you have the convolution. So it's not easy here. You can change this to be, but that doesn't work. So the problem now is how can I get this on a multiplicative form in a meaningful manner with a better approximation? The first thing you should note then is that if I have a likelihood, I can put any prior there, any prior I like. Then I got an associated posterior. And that means I can write this likelihood as the ratio between the posterior and the prior. Since this likelihood is Gauss linear, I put in a Gaussian prior there. The M process comes with steps because there are lithologies behind it. But I do the best approximation with the Gaussian. Then I can compute this posterior, and then I have a Gaussian over a Gaussian like this, and that represents my likelihood. Then you see that I get M there, and I get a linear combination of the D's there, but I got a full matrix there. These are exact solutions, but if I then diagonalize this, I get it on the form that I want, and I have this, and these are some sort, almost the conditional expectations of the pi given all the data. And if I then solve this, then I can go up and down, and I get the full probability of a non-homogeneous Markov chain. And when I sample afterwards, I need only go up for every sample, and it takes no time. And if I put that into my algorithm, I have an algorithm that in the X space of this size goes iteratively like a Gibbs sampler, but every time I go down and I propose, and I have accept to reject with respect to the true model, and I accept actually 1 out of 10 times. And that is more than sufficient to do this very fast. So the important thing here is the approximation of the deconvolution, that I get so close to the solution that I actually can do this by sampling. And sampling then in 3D by this, I do 10,000 sweeps, and it takes only 1 hour on a regular computer in a 1 million grid in 3D. And you see here the convergence is just perfect. It converges very, very quickly, and the proportion of shale is about 0.6, water a little bit less than 0.4, and you see oil and gas is only a few percent out there. And this means I have problems. Looking for rare events out in space is very hard. Most of the models we have seen here with regularization are doomed to fail, because you smooth things towards regression towards the mean means you never hit the big classes, the small classes. In discrete space, regression towards the mean means that you are picking the big classes in front of the small ones. So we see what happens. Well, I will show you some results now quickly. This is the current model. I will also show you results from a model where you have no spatial coupling, only pointwise, no smoothness and no ordering of the solutions, and compare this. This is the results from the current model with context. This red means I go through all the grid nodes. If I have more than 50 probability 0.50 to get sand gas, I mark it red. More than 50% sand oil, I make it green, transparent otherwise. So this is a prediction, a mode prediction. More than that, you have to be above 50%. And you see, these are the wells. This is the calibrating well. You see nicely how the gas is on the top, the oil is under. Things looks very trustable. If I ignore all spatial setting, the complex prior on the discrete case, if I make that the simplest way, only point-wise, it looks like this. The volume of hydrocarbon is much smaller because you have regression towards the large. You have a model which has less structure to it, a simpler model, and you are some sort getting into the big classes. You see up here there is a lot of oil in the middle of the gas and on top of the gas, and it looks like this. These are the 5 blind wells we will look at afterwards. But I have the full probability model. Huh? So now I can do a cross-cut through my reservoir. These are the probabilities. You see it's high probability for oil here and sand and gas here. You see how flat the contacts are, just like they should be. And you see that oil falls just beneath the gas the way you think about it. And then there is some ambiguity in sand and shale. This is what you get otherwise, with no spatial coupling in your process. And you see, you probably imagine some gas here, and they all did in the beginning, but the chances for oil is almost not there. And again, this indicates regression towards the large classes. Then, of course, I have the 5 blind wells. This is from my model. This is from the model with no context. And they look different. Huh? You see they are looking fairly different. The truth is here. This is the truth. And if you look at the truth here, you see it match well. These are the predictions. These are the truth. And you see match well, decent, nothing. Okay, here, only gas, should have oil, only gas, no gas at all. Here, you see that you underestimate the hydrocarbon dramatically in this setting. So there is some trust in this, in the blind wells, that we are able to capture important things. And then, of course, I have probabilities. This is the well, number 2. There's gas, oil, water, shale, and the same over here. And you see how they stand out with high probability, where it is along these profiles in the wells. Here, you see here that I have some ambiguity where the crossover from oil to gas is, and that's because the wavelet doesn't give me exact level, it's on averaging. And down here, things are not very good. This is porosity. I haven't talked much about the porosity model, but what we do is, since we have the lithologies now, we can use different forward models for porosity in shale than we have in sand up to the seismic. So we can sharpen over inversion. And in that way, we got a mixed model, mixed Gaussian model for the porosity. And it looks like this, where you see the contrasts are standing out. But clear, this is what you do, a just linear model from all the way from seismic data through elastic parameters onto porosity. Well, I'm almost there. The important here is that, first of all, when you have models like this, the parameters you put into your likelihood, like wavelets, error measurements, like depth trends, these are highly uncertain. Unless you take this uncertainty into your model and integrate over those, you will never have trustable uncertainty statements. Secondly, 3D Markov random fields are impossible to treat almost if you only go one side up sampling. You have to be able to compute analytically, at least approximately, in the dimension where you have all your constraints. I mean, all the ordering constraints vertically, if I didn't solve that simultaneously all the way down, I would start going in one class and never get out of it again. You have to solve it simultaneously across the most informative dimension. We are able to do that to a good extent. Mapping rare events is very difficult. regularization doesn't help you. Rare events, you really have to shoot and build a model for picking out these small objects that are out there. And you have to have context information about ordering smoothness such that you have pick more information out of your seismic data, because in context you use all the seismic data to support your classification in one spot. And a lot of other things. This can be done very quick. 1 hour, what I've showed you here, we easily get up to 10 to the 8, 10 to the 9 by parallel and also on larger machines. Thank you.
We have one quick question. Bill.
I have a question, it's not quick.
No. But my question is also a bit more involved, because in the beginning you said you calculated the PDFs of the nuisance parameters, and you said, well, I'll only use the observations. You split the observation in the seismic part and the well part, etc. And you said I can do this, but of course you don't have that freedom, because if the observations have influence on the model, then you should use the.
Yeah.
So what were you doing there exactly?
We splitted that in simply because if I did it on the full field with the model parameters, since I only have a lot of the knowledge in the wells, it only has influence for some circular, so it's some computational reasons for it. So we did it 2-step. Secondly, it's easy for me to bring in the wells in the final results and condition them. That's trivial. That's some sort only let the well observations stand there in a Gibbs sampler. Yeah. So, but we wouldn't do that simply because we would see how well we did with the seismic on it.
Yeah.
Okay.